Okay, go ahead, take it away.
Okay, all right, thank you, Bob. Look, thank you for inviting me over to give this presentation. And so I'm gonna talk about MuST, this high-performance computing software package for visual study of materials. I understand most of you are not in this field, are not in the computational material science. So I try to keep this talk accessible to everyone. You can just ask questions if you have any questions. No problem to interrupt or put it in the chat. Bob will handle and will help me to answer questions while I change slides. Okay, so the outline of this talk. First of all, I'll give you a brief overview of ab initio electronic structure calculation. So what is that about? Just so that you can be prepared for the rest of the talk. So what is MuST? So actually, it stands for multiple scattering theory approach to the Kohn-Sham equation. I'll explain what Kohn-Sham equation is about. And it's used for study order structures, which is not that interesting because it's being studied by many people. And what's most interesting part is it is able to study disorder structures like random alloys and strongly correlated systems driven by disorders. And I'll then mention about petascale performance of this software package. So finally, I'll give a summary. Okay, so this is about the outline of the talk today. All right. So talking about computational material science. So what kind of question? Kind of question we try to answer? Just imagine imagine there's a wall there. There's made out of building blocks, and the blocks are glued by whatever the material you're putting there. And it turns out, you can imagine each block is an atom, and what is gluing together is just electrons. Actually, atom is mostly major space occupied by electron cloud, and the nucleus is really occupies very tiny spot. So the major space are occupied by electrons. So electrons really play the role in determining how strong the material the wall is. So the physical properties of matter, such as whether it is metal or non-metal, magnetic or non-magnetic, its mechanical strength, and so on, are more or less determined by the behavior of electrons or electronic states. So the majority of the space, because the majority of space is occupied by electrons. So so-called computational material science goal is try to solve the electronic states so that we can determine the properties of the materials. Okay. All right. So look at the materials, pick it up, and take a deep look of it. So basically, it's made out of many electrons, right? So you have a nucleus. Even though it occupies it's a very tiny space, I make a big ball representing a nucleus. And electron is a red dot, and it just consists. The whole materials consists of these two things. All right. So electrons just kind of moved around this between the nucleus. It turns out it's very difficult to solve. This involves electron-electron interaction and the electron-nucleus interaction. And it turns out it's a many electron Schrödinger equation to solve quite mechanically. So it's a many-body problem. So it's impossible to solve it. So thanks to this great gentleman, Professor Walter Kohn, who got a Nobel Prize in chemistry. He invented density functional theory to solve this problem, so that many-body problem can be reduced to one electron problem, one body problem. That one electron is moving around in this kind of effective field, effective potential that represents the many-body effect. So it turns out this kind of electron is moving in a kind of swamp described by this potential called effective potential, right? So the goal is to solve this so-called Kohn-Sham equation. So this is a one electron Schrödinger equation now, except we need to determine this. So let me turn on my pointer here. Maybe useful. Spotlight. Yes. Okay. Okay. Oops. The light is not on. Let me do that again. Spotlight. Okay. Sorry. So basically, we need to solve this is a Schrödinger equation. These three terms form so-called effective potential. This is called a swamp. The electron is moving in this swamp, right? So that swamp represents the effect of the original many electron effect. Okay. So basically, we need to solve this problem. Okay. So the goal is to, by solving this equation, is to construct so-called electron density, so that once we find this electron density that satisfy this equation, we should be able to answer the questions. What's the energy of this original many body many electron problem, many body problem, right? So that's the goal is to solve this equation, and this rho is the original many electron system, and so we should be able to be allowed to do that. So our goal is to solve this so-called Wang electron Schrödinger equation. Now that original three terms are put together. It's called V effective. That's called swamp, right? So we're going to solve this equation, and originally, of course, we don't know what that is. We have initial guess, and then we solve this equation, find the so-called Computational orbital. We take a square and sum over all the different states and get an electron density. Of course, this is kind of it's not a final solution yet. We use that electron density. We determine this new effective potential, that new swamp, okay, because it is a function of this rho. And then going back to this equation and to solve it. So we have to take this cycle until this whole thing get a consistent solution. In that case, we say it's converged. So of course, we use this atomic units, by the way. And so that's the factor in front of this nebula just disappear, become 1. So this alpha represents so-called Computational orbital index. In case you have a question about what alpha is. So if the whole calculation is consistent, is self-consistent, we say it's converged. That is, then we can go calculate the ground state. In that case, it's converged. The rho will be the ground state electron density. The ground state total energy of the original material, the many body problem, we can calculate it using this formula. Right. So this is the whole idea about how to perform electronic structure calculations based on a density functional theory, and this is just so-called ab initio electronic structure calculation. Okay. It turns out we have many users in doing this kind of calculations, all using different ab initio methods. There are many ab initio methods available. Actually, they all differ the way how to calculate electron density, right? So the most popular approach is called the band structure approach. It's by just solving this equation. Okay. Then there's one particular approach which is very popular. It's called pseudo potential method. You may wonder that this equation may be kind of easy to solve given the modern numerical or the methods available. It turns out it's a non-trivial because the this called a swamp potential here, the effective potential, contains the electrostatic potential given by nucleus. Those have a 1/r effect. So it's a kind of can diverge close to the origin of where the nucleus is. So it turns out it's this because of that. This equation turns out to be it's non-trivial problem to solve. Okay, and this is a kind of three-dimensional problem. The material extends to the entire space. So this turns out it's not easy to solve. So one way to simplify the problem is to use using so-called pseudo potential method. That is, replace those nucleus by certain pseudo potentials, so that this 1/r effect can be smeared out near the origin of each atom nucleus. So basically, just kind of rewrite this equation and convert it into a different equation that we're hoping to get electron density, which close to the real electron density away from the nucleus. Okay, so this is a kind of a pseudo potential method. Because using pseudo potential, it allows you to establish using basis like a plane wave as a basis. Otherwise, without using pseudo potential, plane wave basis is not going to work because near the origin, of each nucleus, the electron density becomes very sharp, there's very sharp peaks. Those cannot be represented by plane waves. But once if you do pseudo potential, those sharp peaks will go away. The charge density will be smeared out near the origin. So that allows you to use a plane wave as a basis. Okay, so that's a very popular method, and you will see a lot of users in supercomputing centers, and they're all using either VASP or quantum espresso or Abinit. It's all based on using the plane waves as basis and based on pseudo potential. Okay, those are kind of methods under that. And there's other methods available. People have used like a multi-grid and finite elements or other multi-grid methods, right? Not using plane wave basis. Not very popular, but they're available. And there's another category. It's called all electron method. It's not using plane waves, not using pseudo potential. It just try to solve this equation directly, and it takes into account that fact that around a nucleus there's a 1/r effect by the point charge, the positive charge contributed by the nucleus, right? So it just solve this problem directly. So you're gonna have to this is so-called all electron problems, because not only consider the so-called highly bounded so-called core states, core electrons, but also these valence electrons, which moves around the entire space. Okay, so both core electron and the valence electrons are treated on the same footing. Unlike pseudo potential methods, the core electrons are not there because the pseudo potential effect. So there's no core electrons, only valence electrons. But the all electron methods rather going to solve this equation directly, just this Computational equation, and there will be core states need to be treated. So kind of the typical there's a method called FLPW method. The software developed for this based on this method, like Win2K, ELK, and the Fluor and the Flare. All these packages are developed in Europe. For some reason, the Europeans are very good in developing those softwares. Also, like VASP, Quantum Espresso, Abinit, all developed started in Europe. Anyhow, so FLAP is one of those all electron methods. Another method is called KKR method, and MuST, what I'm going to talk about is a KKR method, and it's a package name, and there's other packages also there, but not publicly available. Jülich KKR, SPR KKR, these two are developed in Germany, and Akai KKR is developed in Japan. And these three are not kind of public code. KKR method is also known as multiple scattering theory approach. And theoretically, it is trying to give the exact solution of the Computational equation. Okay. There's also other methods available, LMTO and EMTO. Both are derived from KKR, and etc. etc. Maybe I'm not aware of, but there's another approach besides band structure approach, which tries to solve this differential equation. There's another approach is called Green's function approach. It tries to calculate Green's function of this Computational equation. Okay, so instead of just solving this differential equation, but rather we can calculate Green's function of this Computational equation. Why is this useful? Because if we know the Green's function, by taking the imaginary part of the Green's function, which integrated from the energy, then what you get is electron density. That's what we want to calculate. So if you know the Green's function, we should be able to calculate the electron density instead of just solving this Schrödinger equation and construct electron density this way. Right? This is another way of doing it. So so Green's function has certain advantages, and fortunately, there's only one way to calculate Green's function, which is given by KKR method. So KKR method can do both. Either you do band structure calculations, they try to solve this equation, or you can calculate Green's function, and you can calculate charge density. Okay, so both KKR can do both. Okay, either way, it turns out Green's function is has very unique properties and gives certain advantages in terms of performance. All right, so I'm going to explain what is multiple scattering theory a little bit from solid to atom, from top down. So of course, in the density functional theory, as I explained with this LDA or GGA approximation, enables us to find electron density of ground state of solids. Right? So to achieve this, as I have explained, we solve Kong-Shan equation, or we calculate Green's function, which is one electron Schrödinger equation with effective potential. Right? This is called swamp. Okay. So if you look at this solid state material, it's made of it's atoms, right? So which having this effective potential fill up the whole entire space. What you can do is we divide the space into domains. Each domain contains one atom. All right, so we divide that, and then we can domain 1, domain 2. We can call it omega, and omega n. Right, so the whole space is divided into domains. Each domain contains atom. Now we start to take a cut, take another cut, and take another cut. We take that little piece out, omega n out. All right, that piece just little puzzle, taking that out. So what's inside? There's a potential inside. That potential inside, and this R sub n is kind of, I use the atom, this nucleus as origin. I take that as an origin. So this R sub n represents a vector starting from that origin. Okay, that's a local origin. So what's potential inside is just effective potential in this domain. Okay, but outside is 0. All right, so I just take the piece out. So this potential is defined to be 0 outside this domain, and inside is just this swamp potential. All right, so I do the same way. Of course, each domain has its own potential. Yeah. Then, of course, you add them all this together is just effective potential for the whole space. Okay, this original swamp. Because of that, I can treat this as a single side scattering potential. I can consider that as a domain as a single side scatter the electron, because that's the potential electron field. So that will be the electron is scattered by that potential. And in the scattering theory, this single side local potential can be used to calculate a scattering property of that domain defined by a so-called T matrix. Okay, so that's a kind of fundamental quantity we need to calculate. All right, so the multiple scattering theory is also known as KLCPM method or Green's function method. Is the way in our view is that the Kong-Shan effective potential, which is a swamp potential, is considered as a collection of non-overlapping electron scattering potentials centered at each atom. Right. So basically, that's what I explained in the previous slide. So the whole domain is divided into whole space is divided into domains. Each domain contains an atom. Okay, so Kong-Shan orbital wave functions are the standing wave solution of one-electron multiple scattering processes. So that's basically it's a condition I apply to the scattering problem. So by applying this condition, I'm able to calculate. I'm able to determine it's become a multiple scattering problem. Right, electron being scattered by many scattering domains. So it's a multiple scattering process. So apply this condition, that the standing wave condition. So I'm able to determine so-called kind of circular equation-like things. So that will allow me to calculate band structures, or we can calculate the Green's functions that allow us to determine the electron density. So entire process is the following: that given each domain, for example, Vn is a potential in that domain, I calculate the scattering property of that domain, a T matrix associated with that particular atom, and then that's called single scattering matrix. Use that, I can calculate the multiple scattering matrix tau that allow me to calculate Green's function. With the Green's function, I'm able to calculate electron density. That's all I want. Right? So that's a kind of a different approach in contrast to band structure calculations. Okay, so then what is MuST? MuST stands for multiple scattering theory, because I just want to have a name that everybody can remember. So multiple scattering theory is a method for solving the Kong-Shan equation, okay, as I explained in the previous slide. So specifically, it calculates Green's function or Kong-Shan equation and determines the electron density by taking the imaginary part of the Green's function. So MuST is a computational tool for initial electronic structure calculations, And it's so-called evolution implies that the electronic structure is determined based on fundamental physical law, which is in this case the quantum mechanics, rather than empirical models with adjustable parameters. So there's other individual software packages like, as I explained in previous slide, like VASP, N2K, ELK, Embedded, and Quantum Espresso, and etc., which are based on different methods, right? So multiple scattering theory is one of the methods, individual method. Okay, so we have made this available, this software package available. You can get it by git clone. It's available on GitHub, so you can get it by taking this from using Git. All right. Once you do that, a directory called MuST will be become created on your local space. Right. So this whole project is a 3-year project funded by NSF CSSI program. So involving people from CMU, LSU, MTSU, Oak Ridge, and also our collaborators from Germany and China. We're trying to establish a computational framework based on scalable approach to first principles studies of random alloys and disorder effects in quantum materials, and build upon the research codes developed at the Oak Ridge and PIC. The embryo codes basically is a KKR, CPA, and the LSMS. I'm going to explain what KKR, CPA is and the LSMS is. And we're also going to integrate DMFT and other effective medium methods developed by many-body physicists who are from LSU and MTSU. We try to build a new software package that allow us not only dealing with standard density functional theory calculations, but also be able to incorporate like strong and correlated systems using many-body physics methods. And so this is available as I show up in the previous slide. So the contributors to this project have been we have many other people contribute to the effort. Some are actually it's a ECSS project, and we also have a wiki page that to know more about this project. You can see this GitHub, this wiki. You can visit this place. MuST, M-U-S-T. I don't know if that matters. Should be this ST should be capital. Also, we have a YouTube channel because every week we run a kind of seminar, and participants will talk about give kind of pedagogical discussion, kind of education about the methods, many-body physics and the empirical methods. We try to educate one another because it really involves people from all different backgrounds. And so we have a YouTube channel running, and we have attract many viewers. If you're interested, you can go take a look this YouTube channel. Okay, so we have applied this code to the study of standard ordered structures, like for example metal. Like
yeah, before you go on, we have a question in the chat from chat.
Okay. Go ahead. How do I view the chat? How do I let me see? How do I view this chat?
You should see 3 dots.
Yes. Oh yeah, I see it.
Yeah, and if you click, you should be able to see the question.
I'm not in this field, so have a very basic question for solid. Please explain a bit the basic assumption that atoms are equally spaced. Okay. No, atoms are not really equally spaced. So I draw that just for pleasure of viewing. In practice, metals in principle, metal are in equally ordered structures. Atoms are have an equal space, but in practice, if you increase temperature, atoms will move around. Or for random alloys, some atoms may occupy. You can actually allocate more space to one atom than the other. Okay, doesn't have to be exact same space. Okay, all right. Okay, good question. Thank you.
It says Mona, did that fully answer your question?
Yes, thank you very much.
Yeah, and I think it's getting at the idea of periodicity.
Yeah.
Right. Okay. All right. Go ahead, Yang.
Okay. Thank you. All right. So this is a kind of application of this package. We'll take a look at a simple metal, molybdenum, for example. We can compare results with other codes and with the experiment.
Yang,
Yes.
thank you very much. It was very interesting talk. Would you please put the YouTube link somewhere in the chat if possible, or send us with either like Slack or wherever you think better. I want to go and look at your YouTube channel if possible.
Okay. I'll try to do that after this talk.
Yeah. Anytime. Yeah.
Okay.
Yeah, it was very interesting.
All right. Sure.
Thank you very much.
Okay. Yes. So we this is a kind of a simple application of this package. Just verify this code works as should be. All right. So we made a comparison with other methods. Another way to verify this, we just calculate force acting on the atom, and so we compare with other calculations. Right. So this is a kind of a plot of compare with VAS, compare with quantum espresso, because force calculating is a very it's kind of it's a very strong severe measure test of your code, right? So we'll compare with pseudo potential calculations. But remember, this is all electron. Okay, so make this comparison. Anyhow, so but doing this is just like everybody else. We can do things, but we can go beyond. We can do things much better than other methods. Like we can do fully relativistic calculations for materials. So recall what is why we need a fully relativistic calculation. For example, we think about a Bohr's model for atom, right? Even though we know Bohr's model is not right, but it gives a kind of simple physics, simple explanations. So in Bohr's model, electron has this called Bohr orbital, depending on which orbital radius, right? R sub n is the radius of the electron, depending on which orbital you're talking about. So the higher orbital, the further away the electron is. So this basically, on average, give you a radius, and the speed of electron is given by this, right? So this different orbital that have different speed. The speed is proportional to the atomic number. All right. So in particular, if n equal to 1, so the first orbital, so look at this equation that v sub 1 equals alpha is called a fine stretch constant. It's 137, if you remember. That's from modern physics. Proportional to z is proportional to c, right? C is the speed of light. So obviously, okay, of course, because of this constraint, speed cannot be greater than speed of the electron cannot be greater than c. So z cannot be greater than 137. Right. So basically, it tells you the atomic number cannot go beyond 137. Right. That's the kind of simple thing. But anyway, so the higher the atomic number, the higher the speed. Right. So if you will see that as the atom getting heavier, the speed of electron getting very, very high, close to the speed of light. So obviously, relativity becomes important. And if you take a look at the relativistic effect, the radius you have to take into account the length contraction effect, right? So obviously, the bonding is kind of shrink because of relativistic effect. Okay, it turns out it is true that there's many relativistic effects play important role for material properties, like for spin optic coupling effects, or magneto-optical effects, or bond length contractions. And you may wonder, the color of gold, it turns out it's a relativistic effect. Z equals 79, obviously, for that heavy atom, relativistically become important. So a color of the gold is a relativistic effect. Another interesting effect is why mercury is liquid at room temperature. It is also a relativistic effect. All right. So obviously, relativity we need to take into account for heavy atoms. All right. So in that case, we have to solve the so-called Komshan-Dirac equation instead of Komshan-Schrödinger equation. Right. The equation I show you is the Komshan-Schrödinger equation, but we now have to solve the Komshan-Dirac equation. So in MuST, we have that tool built in. So one of the interesting investigation is called polonium, which is discovered by Curie, Marie Curie, I believe. Z equal to 84, which is very heavy, and is highly toxic and radioactive. So that's very, very little experiment has been performed on this material. And we know that it's a very only element in periodic table that has simple cubic structure in at room temperature. Okay, unlike other metals, they all either FCC or BCC or structures, but this is a simple cubic structure. It's very unique. And it turns out it's believed that the structure is driven by relativity. So we did relativity KKR calculations, and I'll jump this. So we did all this this little details. So we plot the total energy versus the volume, and that will give us the equilibrium volume where the energy is minimum. Okay, so the determining the lattice constant. We plot that, made the calculation for different structures. So it turns out simple cubic has the lowest energy. So simple cubic is the ground state for polonium. Okay, I guess I will have to rush up. All right, so more interesting part is we can do random alloys. So there are three different approaches to random alloys. One is the supercell approach, is you construct a big unit cell that to mimic the random alloy. All right. So we have the tool called the LSMS method. It's a linear scaling approach, so that we can do more than 10,000 atoms or more in a large unit cell to mimic the random alloys. Another approach, which most other empirical methods can do, is by so-called cluster expansion approach. Is by generating a set of typical small unit cells. All right. Then you give weight to each small unit cell and do the average. You calculate, do the calculation on each small unit cells. Right, and then do the average. Hopefully, then you get an average total energy. Because of that, we can do this called SQS method, which generates a bunch of typical small unit cell structures. We can combine that with our ab initio method, KKR. Okay. So the third approach is called effective medium approach, with coherent potential approximation, which can only be done with this method, with a Green's function approach. So okay, KKR CPA. Right, so I explained this LSMS and KKR CPA. Oh my! All right, so so for LSMS method, that is for a big unit cell, we can around each atom in the unit cell, we draw a big circle. We only consider the cluster around each atom. Okay, so they call it LIZ for this particular atom. We take that we do that same thing for other atoms as well. We do that for each atom in the unit cell, assuming that we have a large unit cell. And then we only treat that cluster. We try to calculate the multiple scattering matrix for the center atom. That be used to construct the Green's function around that atom. So that will be used to calculate the charge density around that atom. So that's the idea. So computational cost, it only depends on the size of this big cluster instead of this entire unit cell. Okay. So the computational cost will be proportional to the number of atoms in the unit cell instead of cubic scaling. All right. So this basically that's the kind of things we need to calculate. So the computational cost that's dependent on the size of this cluster. All right. So this method is made a linear scaling by just ignoring the for each cluster we ignore the multiple scaling effect beyond that the region of that cluster. So computational cost is proportional to the cubic power of the number of atoms in the cluster, but it's linear scaling to the number of atoms in the unit cell. So that unit cell can be made very large. So it is intrinsically parallel because we can do that for each atom for the in the unit cell. So that's kind of intrinsic parallel over the atom in the unit cell. Allows the ab initio calculation for even more than 100,000 atoms. This has winning many prize, teraflop and petaflop performance prize. And it's been chosen by DOE as one of those exascale computers application readiness for frontier computers. Okay, I need to rush. I have about 5 or 10 minutes. Okay, so okay, I'm going to jump this. Okay, this is kind of one of those applications using LSMS together with a machine learning technique that to study high entropy alloys. That you can use the LSMS method to generate many supercells to train data, to allow to generate training data. Okay, this is done. You can find this publications. So this is using a Bayesian ridge regression method. Each consists of like this 200 training data. Each data is a 1024 atom unit cell. calculation. Okay. Anyway, so magnetic material. There's another application of the LCMS by generating many samples. Each has its own magnetic complex magnetic structures. So it collects all the data using a Monte Carlo technique to run the average, and you can use to determine the magnetic phase diagrams. So this shows determining the transition temperature of iron. So it runs like it achieves like a petaflop performance on Titan. Scalability. This is the performance on Titan using with GPU enabled. Sorry, I have to run a little bit rush because I used all my time almost. So this is a weak scaling of LCMS on the Summit with a GPU performance 98% of a full machine performance. Okay. Anyway, so all right. So now I need to explain what KLCPM method is. Another approach to disordered structures. This stands for CPA stands for coherent potential approximation. The way we do that for random alloys is what we need is to find so-called effective medium, CPA medium. What it is that consider a random alloy. There's many different configurations. So the idea is we try to find its average of the configuration average of the random alloy by finding this so-called CPA medium. And that represents the configuration average of alloy. Okay. So the question is, how do we find this effective medium? This CPA medium. So the effective medium, so-called effective medium atom, is represented by a T matrix, a scattering matrix. Okay, the goal is to find it. So how to find it? So we make a so-called single-side approximation. The way we do that is we put a real atom A here, and surrounded by the effective medium, or put a real atom B here, surrounded by effective medium. The average is supposed to give this. So this is kind of self-consistency involved, but the unknown is the effective medium, the scattering matrix. Okay. So this is kind of single side approximation. So once we can do that, we can do we can calculate Green's function for this system and calculate Green's function for this system. We do the average. That's the average of Green's function. That gives you the average electron density. So each of this represents a single impurity problem. It can be calculated with the one atom per unit cell problem. It can be one atom per unit cell calculation. So if this electron density for this. Each of this can be calculated using taking the Green's function, taking the imaginary part, and we can get the average electron density. All right. So that's the goal. We can take a copper zinc as an example, which is known as called brass. It's a typical a random alloy. It has a long history of brass. This structure can be ordered structure at low temperature, or can be a disordered structure at high temperature. And the transition happens at a 730 Kelvin degree. Then for the ordered structure, so a B2 structure is look like this, right? So at the corner of the cube is occupied by one type of atom. The center is occupied by the other type. It's called B2 structure. Or disordered structure, each side is occupied randomly by either copper or zinc, right? It's called a beta phase, or this is called beta prime phase. And we can do the calculation for this disordered phase, with varying the lattice constant. You can use the KLCPM calculation. What you get is a kind of plot of the total energy versus the lattice constant. The minimum corresponds to the equilibrium lattice constant. This is done. Remember, this done by KLCPM. This is calculated with one atom per unit cell with KLCPM method. Okay, so that's very powerful. Unlike other methods, you have to do a supercell. You have to big run many atoms to mimic random alloy. But for this KLCPM, you only have one atom per unit cell with this approach. So it's very fast. Even further, you can do a hydrogen alloys that you can have many elements. In that case, supercell will become inappropriate because when you have many elements, some elements the concentration is not really nicely determined. Maybe, so for example, the 0.3333. Then how many atoms you need in your unit cell to represent that kind of content? It becomes very difficult. So we use KLCPM to do that. The concentration of each element can be fine-tuned. This is a result. It actually turns out to be calculated. This is a kind of ECSS project. One of those ECSS project calculation. The student did this calculation with KLCPM to study the hydrogen alloys. You can compare with your experiment, and this is spin-polarized calculation with only one atom per cell calculation. So the KLCPM is a very powerful method. I just want to mention, and also we have like a user community engagement effort is by collaboration with Widom and his student from physics department at CMU. We kind of improved KLCPM method by including showing order effect by establishing kind of neighboring atoms which depend on central site atom properties, so-called shortening order effect. So because in random alloys, sometimes unlike atoms like to stay next to one another. Sometimes like atoms like to stay one another, called a short energy clustering. Short energy ordering means that unlike atoms like to stay together, right? So that kind of effect needs to be taken into account. So we developed this new method and made a publication. So I will not have time to explain that. I'll have to jump. And so we did this calculation with copper zinc also by including short energy order effect. We did find there's effects with energy and also density of states. Okay. Because I'm running out of time, but I want to mention this that there's a short YouTube video also created by ECSS champion, campus champion, Dr. Helen Kershaw from Brown University. She set it up, and so with YouTube, you can learn how to use this package, MuST. She developed that for a summer workshop last year for training undergraduate students. So she set up this tutorial example that once you download this package, you'll see the tutorial example to study copper zinc. With different structures, either ordered or disordered. So you can compare their energy to determine which one has a lower energy, right? So you can run this kind of examples here. It shows how the example is running. You can do the same thing with other structures. Okay, so you can run 3 different samples. One is a complete disordered structure, and you get the energy. Another B2 structure, another is a supercell structure, a kind of arrangement of atoms. It turns out the B2 structure has a low energy, so that agrees with experiment. At the temperature, at lowest temperature, the copper zinc tend to be ordered structure. So disordered structure is the energy given by this. You can use a kind of very naive approach to estimate what's the transition temperature by using delta energy, which is the energy difference between ordered and disordered, and divided by KB. You can estimate it's not exact, but close to 740 degrees. That's the we know that's the transition temperature, right? So this is kind of a very interesting approach. It's a good thing material for undergraduate student. Okay, so next thing we have to do is I have to jump. I'm running out of time. So this LSMS with the embedding that we want to embed instead of in the vacuum, we have to have an embedding effective medium, which takes into account strong correlations of electronic structure correlations because of many body effects. So this is kind of collaboration with many body physicists. So that's our kind of ongoing project. We try to capture the Anderson localization effect driven by disorder. So we kind of combine the power of LSMS, this abelian method, together with many body physics method, typical medium method that combine the two together, we should be able to treat quantum material, to study quantum materials driven by a disorder. So this is our ongoing project. So I will not, this is a kind of a model calculation. We just show that this approach will work, but this is our model calculation. We want to develop our abelian code so that we'll be able to apply to the real materials. Okay. So that shows that if it was typical medium with disorder, you see this there's a metal insulated transition here. The density of states start to decrease. That means the material start to become from metal and to an insulator when you introduce a disorder in the material. Okay. So this is done with a model calculation. All right. So anyway, so finally, I want to give a little summary. I'm about finish my time. So MuST code has been become made available year before. So can be obtained. The package can be obtained in this way. The current capability includes mounting full potential, calculating spin polarized, non-spin polarized, and spin candidate for complicated magnetic structures. Can do non-relativistic, scalar relativistic, and fully relativistic calculations, which means that we can solve direct equations. And it does do different functionals using libxc library. The currently under development is that we try to combine with the effective medium embedding approach developed by many physicists. And also we are developing a Kubo-Greenwood formula, implementing Kubo-Greenwood formula to calculate electronic transport in disorder alloys. Okay, this is ongoing, and I have made great progress. Code should be made available soon, and we'll have a student working on this. We also welcome the collaborators and users to participate in this effort to make MuST efficient and robust community code. Okay. Finally, I'm going to sell my book. If you want to know more about multiple scaling theory, we have a book written and available on Amazon, and I'm one of the authors. And it turns out it's quite expensive. Doesn't have to be that expensive, but anyway. So that's all I want to talk. And if you have any questions, please ask.
I'm sorry, I was muted.
Okay, does KKR have high accuracy semiconductor? Good question. About semiconductor bandgap. That bandgap is, it's all, what do we do here, KKR and together with other application methods, all built within the density functional theory, and we take LDA or GGA approximation. So the bandgap essentially has to be, it's an effect of, we have to take into account that there's an excited state. You only have to do like a GW method, or maybe time-bound or time-dependent DFT. You can treat bandgap. In the framework of standard DFT, you're not going to treat a bandgap properly. Or you may argue about including like a hybrid functional, but those are kind of not fully, I won't consider as a fully first principles, because there's a kind of adjustable parameters. It's a game. Yeah, I think there's a better way to deal with bandgap in semiconductors. You can go either with like a GW or with this called effective dynamical mean field theory. This is a many-body theory. It's also ongoing project which has been implementing into VN2K code. It's by a group in Rutgers. They are doing that right now. That's a better way to deal bandgaps, not in the framework of DFT. Rather, you have to extend a DFT. Yeah. KKI is just only one of those arbitration methods in the framework of DFTs. So to treat bandgap, we have to add other many-body effect, many-body tool to it.
Great. Do we have any more questions? So Yang, I just have a couple of questions. So
okay.
First of all, you did talk a little bit about the scalability of your code.
Yes.
And you like say running on Titan, it's really impressive. How does this compare to other material codes? Is MuST much more highly scalable than these other applications?
Okay. So far, I'm not aware of other real linear scaling code. We are scaling with number of atoms in it. Other arbitral code, they have certain scaling is, they can say they can run on a whole machine, but the number of atoms is not that many. They are constrained by, say, if they use a Fourier transform, they're constrained by fast Fourier transform. There's no way you can scale it up. But we don't do Fourier transform. We have local basis. So also, it's physically in terms of physics, we made it linear scaling with number of atoms. So this scaling is in terms of number of atoms. I'm not aware. I know there are many other efforts, and but this is the only real code can do linear scaling in terms of scaling with atoms.
Okay, so when you say scaling with number of atoms, essentially that you're getting perfect weak scaling.
Yes.
Okay, great. Which means that you can also solve much larger, much more difficult problems.
Yes.
Okay, great. Do we have any more questions before we wrap up?
So, Yang, this is Sudhakar. Yeah, so thanks, and it's nice, nice work. So, does this code also treat the like a mixed mode things like phase diagrams, or can deal with grain boundaries where there are mixed microstructures?
Okay. For that phase diagram, you have to integrate. We have to combine with some statistical physics method. There's other statistical physics method, like you can do a Monte Carlo, or you can do like a you have to combine with some statistical physics method to do to study phase diagrams. This only give you the energy for one particular configuration, or say you can do CPA method. You can do a kind of average the energy for kind of random alloys. For really study phase diagram, you might want to have to combine to use a statistical physics to help you to determine the phase diagram. Because you see, what we have done here is only temperature 0. Okay. For the grain boundaries, then yeah, you have to, usually what people do is they construct a large unit cell to build in like an effective grain boundaries. Yes, that will use the supercell method. We'll do that for you.
Okay.
Yeah. On the other hand, for CPA is for the random alloys that you have an underlying lattice. You don't have like dislocations or that kind of things. Okay. It's a perfect for there's an underlying lattice problem, but but atoms are randomly distributed on the underlying lattice.
Thank you.
Thank you. So we're now at the top of the hour, and I see people are beginning to drop off for their other meetings. So Yang, again, thank you for that great, highly detailed talk. I'll get in touch later to make sure we get your slides so we can post it online along with the recording. And for everybody who joined us today, sorry for the mix-ups in which coordinates we're using. This was something that was dropped on us over the holiday weekend. So in the future, be sure to use the link that I send out in the announcement emails, and also on the ECSS Symposium page. Those are the correct coordinates. So great, thank you very much, and hope to see you all in March.
Okay, thank you.
Thank you. Thank you. Bye-bye.
Yeah, I'll remember to post that YouTube.
Awesome. Thank
I'll
you
send
very
you
much.
YouTube. I know you know that you want to know it, so I'll send it.
Sure. Thank you very much. Yeah.
Okay, thank you.
And it was a great talk.
Thank you. Bye-bye.
Perfect. Bye-bye.